down just to remember, since I didn't record. So of course, sometimes please, when we are in presence, remember always, because I forgot because we talk. So in consolidation, we said, just to synthesize, that is a big phenomenon. A big phenomenon that can be, studied with important relationships and with a lot of complex theory. One of the most important theory is the one from Bishop in 1973, that gives the values of B that depends, of course, on three parameters. One is the compressibility of the fluid, the compressibility of the soil, and the compressibility of the total volume. This relationship that is correct has been modified, simplified by Terzaghi, and we call the Terzaghi principle, except definitely this relationship that correlate the total stress inside the soil with the intergranular stress and the pore pressure. This relationship can be used, may be used in our applications always, but we have to remember that there could be some cases, very rare, when this relationship cannot be used because the difference between the compressibilities are not so large as Terzaghi considered. But for our followings, for this course, you have to remember these equations. Instead, the other important thing that I was telling here is the conservation of mass. And conservation of mass is a principle that is basic of every mechanics physics problem. And here we have a three-dimensional element of our soil. And we have to consider the velocity of the fluid. And so if we consider along all the three directions, along Z, Y, and X, we can see that the things that enter, the mass that enter from this phase has to leave this phase, plus the difference that is this delta N, the porosity, per, of course, the densities of the fluid, per the velocity along Z axis. The same happened for the two, and I was here before the registration, the recording, and then the same happened for the other two directions. So we are able to write an equivalent relationship for the x-axis. So we can see here that the difference between these two terms again is this delta n per v per delta n per rho f, the density of the fluid, and vx. And in this other case, the difference is again these terms. That is the, of course, relative between what enters and what leave the 3D elements of soil. So the equation of the conservation of mass of the soils and the fluid can be established considering the flow into and out, so into and out of the elementary volume fixed in the space, and the mass of the fluid, of course, is the elementary volume that is called N, the porosity, rho F per V. What we call the increment of this mass per unit time is determined by the inward flux across the surface of the element. So we consider the flux that enter and leaves the element. So, for example, as I said, we can write the equilibrium, the conservation of mass in the y direction, and we can have here delta n rho f per v y per delta x and delta z, that is, of course, equal to this part, as we said, because this is the volume of the our element. So if we consider V as the volume, that is, of course, the multiplication delta x, delta y, and delta z, we can write these as this, you can see here. Of course, it's very simple because V is delta x, delta z, and delta y. If we put the ratio delta y, we eliminate delta y here, and we have delta x and delta z. We can write this, of course, in terms of infinite and not of course, delta. And we obtain this formulation. You can see these terms here. It is this. Again, if we consider the three direction, similar terms is for the z direction and similar for the x direction. And of course, this instead, see here, is the mass that is cumulated at the delta t inside the soil, the solid. So here is essentially the volume that is cumulated inside the mass of the solid. So you can see here that we have four terms. The first depends only on delta t without any velocity because is inside the solid. These three terms are similar but not the same, and they depend, of course, on velocity x, velocity y, and velocity z. So this means that the first is the mass cumulated along x direction. This is the mass cumulated along y direction, and this is the mass cumulated inside z direction. Do you have questions? Okay, so we can rewrite this formula with the gradient. I don't know in Spanish. This is the gradient. Is the it means this symbolum the same as the sum of these. And at this point, we can also call the compressibility of the fluid that can be expressed by considering the constitutive equation of the fluid, and so we a sort of when in structural mechanics we consider the Young modulus, and so the relationship between the sigma and the stress, the sigma and the epsilon. So we can write something similar while we consider rho f that multiply Cf. And so we can rewrite all of this first in this way, and then it's not important that you remember this part, but this you can see here that we have, if we derive this into different part, we have delta n ratio delta t plus NCF that multiply the pressure ratio T plus this part that is the same that we saw here. So this depends on the volume on the space, and this part depends on porosity and the time. So a term expresses the product of the fluid velocity and the pressure gradient has been disregarded, assuming that both are small quantities, so that the product is of the second order. So we can consider this. And at this point, we can introduce the balance equation of the soil material. That is, so if we consider only the soil, that if you remember is the one that we saw previously. So 1 minus n rho s is this quantity. It is now assumed that the density of the soil particle is a function of the isotropic total stress sigma and the fluid pressure P, that is what we already seen before, so that we can write at the same time the relationship between rho s and rho s CS, as we saw in the theory of the consolidation here. Remember? And so we can write all the previous, if we introduce this and this inside this formulation, we arrive to define this that is still very complicated. In fact, we can also work on this, and where again a term expressing the product of a velocity and a gradient of stress or pressure can be disregarded again and put together, you see this into this, we obtain finally this, that is the gradient of W, the velocity, the velocity in the soil, the gradient that multiply n per the difference of the velocity plus the difference of the compressibility that multiply rho p, the derivation of p in the time, plus cs that multiply the stress in the time. And so this is what we call the conservation of mass that include also the consolidation problem. Before going on, tell me if you have some questions, please. I drink some water in the while. Of course, as I said, we will see on Tuesday how to apply all these, but these are fundamental, of course, are the equations that are fundamental for our studies. So again, we can call, this is the final formulation, so no more formulation we will take after this, but we have to consider, this is important, that the quantity n that multiply the difference between P and W is the porosity multiplied by the relative velocity of the fluid with respect to the solid. But this is what we generally call in the let's say the typical behavior that happens in a fluid when a flow goes inside the fluid and goes from one side to the other side of the soil. We have what we call a flow of a fluid through a porous medium that is often defined with Q. Q is the flow that, again, goes inside a solid that is can be considered as a porous medium. And this formulation is generally considered called the Darcy law that we will see later. But for now, it is important to consider that Q is, as we said, the flow of a fluid through a porous medium. So if we consider the difference between the velocity or the relative velocity multiplied per n, multiplying the porosity, we can have that Q is our flux. And also, if the displacement vector of the solid is, as we do in mechanics, in structural engineering, U as a displacement, the term gradient W can be rewritten in this way by applying, as I said, the valence strain, and so everything will be changed into epsilon equal the gradient of U as happen in mechanical engineering, civil engineering, structural engineering. So the epsilon is the gradient of the displacement. We can rewrite everything in this way. So we can have the delta epsilon in T, respect to delta T, plus the flux multiplied per P ratio, the delta P ratio delta T, plus this that depends on the compressibility of the soil, equal to the flux. This is, again, the most condensed way to rewrite this by considering, as I said, these two more, let's say, principles. One is the flow of fluid defined by the Darcy law, and this one with the epsilon, that is, as again, the gradient of U, of the displacement. We have some questions, guys, here.
Professor, is there any maybe a good references that you recommend to read about these formulations? It might be very helpful for us to take a look at some background, but it might be even better if you can recommend the reference.
Yeah, you mean some books?
Yeah, like maybe some book of that might have the best way for us to have the context of all this information. That would be very helpful.
Yes, in my opinion, as I said before to Francisco, the second part of the course, the more related with soil structure interaction, is definitely contained in a very famous book that is the book of Kramer, Geotechnical Engineering. So that will be no problem at all, but it will be in English. This part instead, as I said, as you discovered very soon, I took from an Italian book, my book that we use in geotechnics. So I guess you have something in Espanol as well. So in my opinion, it's better if you took a look directly to a Spanish book with the same things explained. Again, I have to tell you honestly that you will find a lot of pages on this. That will be helpful, but of course, to understand every detail. And on the other side, again, the scope of this course, of course, is to understand what we do, of course, but is to apply this formulation. So again, for now, I know that I'm only giving you information, but please wait and you will see how to apply soon this equation. Doesn't mean that you don't need to understand, of course. But yeah, if you need some books, my recommendations is in something like geotechnics. I will, if you want, check in Espanol, but I'm sure that you will find something.
All right. Thank you, Professor.
So this is the conservation of mass, and now we have to do another pass just to finish, just to clarify everything. Remember that from here we introduce the consolidation problem inside. But we said before that the Terzaghi principle is a simplification that we can use sometimes. In general, we can use for 99% of the cases. So why don't we use this to simplify this? This is the next step that we are doing. So if we introduce the isotropic total stress that can be expressed with Terzaghi principle, you know what is CM now, that is the compressibility of the porous medium. We can introduce this formulation inside this formulation, and we can rewrite the conservation of mass plus Terzaghi as what we call the storage equation. The storage equation is this equation that put together Terzaghi and the conservation of mass. So remember this. This is the most complex, the most, let's say, I don't want to say perfect, but the most general expression of the conservation of mass plus consolidation. If we simplify the consolidation with Terzaghi, we have what we call the storage equation. The storage equation is a simplification because we are simplifying with Terzaghi principle. So here we can see what we can call the SP, that is store activity, and we can have the first part that is the epsilon, so the gradient of the displacement. We have SP that multiply delta P ratio delta T, and we have the flux. Very, very simple. So it is very simple to remember, and this is what we will use in the application. So again, it's not necessary that you will know all the detail, but what I need you to know is this formulation and the fact that this formulation comes from Terzaghi principle and the conservation of mass, right? Again, here we have three parts, three terms. One is the flux, so connected with this, the space, and these two terms that are connected with the time. So definitely you see this first 10 slides can be reassumed in a very compact and very let's say easy formulation that can be used in applications. And let's see what we wrote. What I wrote. This equation expresses conservation of mass of fluids and solids and may be denoted as the storage equation. So for now, after this course, you have to know, see what I put in red means that you have to know, and in particular, this has to be known as the storage equation. It shows that the compression of the soil consists, understand clearly, of the compression of the pore fluid and the particle plus the amount of fluid expelled from an element by flow. So it means that, as I said here, that the quantity that enter is like the quantity that comes out minus the quantity that is remain inside the element. This for the three axes, for the three directions. So it shows that the compression of the soil consists of the compression of pore fluid and the particles, plus the amount of fluid expelled from the element by flow. A number of assumptions have been made in this derivation. So this is the limit. We are talking about how this formulation is limited. The soil particles and the fluid are linearly compressible. And if you remember, we saw from the first lesson that the soil is not linear. So here we are doing a really big simplification first. Then some second order terms consisting of the product of small quantities have been disregarded. So second simplification. This happened when we consider the principle of Terzaghi instead of all the consolidation problem. But the storage equation can be considered as a reasonably accurate description of physical reality. And this is the formula that you need to know from here to the end of the course. It means that this formulation is like the young, the hook formulation inside the structural engineering. I mean, it is something that we have to know. I don't want to say by memory, but knowing what we are talking about. Do you have some questions? Let me see. 1 second. Okay. Okay, so now the other thing that we are talking about is what I already introduced, that is the Darcy law. In 1857, Darcy, and this is only a law, so it was taken by experiment, found by experiments. Darcy saw that if we discharge a fluid in a porous material, this fluid is proportional to a K. That is what we call the permeability of the porous material and the viscosity of the fluid. So here we can see that the Q that we were talking about here, this Q, is definitely proportional. You can see proportional. You can see here by K, that is the permeability, that is intrinsic of a porous material, and the viscosity of the fluid. Plus, of course, here you can see minus, you can see the gravity vector. So now we want to consider an important thing that will have very important consideration in application, that is called the permeability. That is this K. So the permeability depends, of course, as the name says, on the size of the pores. And in a first approximation, we can consider the permeability K is proportional to the square of the particle size. Saying that, we can consider that if the coordinate system is such as the theta axis, so we consider only the vertical direction of the component of the gravity, this term, of course, is 0 for the x and the y direction. So this formulation can be written the same way without any approximation in this way. You see that G is remained only here, that is in the Z, in the vertical plane. At this point, we can write rho F per G as the volumetric weight of the fluid. And so, in soil mechanic practice, the coefficient of Darcy law is often expressed in terms of the hydraulic conductivity K, that is not the K that we were talking about before, rather than the permeability K small. And this hydraulic conductivity can be defined by this approximation with this product K, that is, as we said, the permeability, per rho per G ratio the viscosity. So at the end, the Darcy law can be rewritten in this way if we consider both these two considerations. One, that we consider the three axes separated, and secondly, that we consider the hydraulic conductivity instead of the permeability. So the Darcy law is the law that defines Q. So this Q now has something that has to be worked on. At this point, we know that delta Q is exactly this, that is the gradient of Q, that, as we say now, it is rewritten in this way, and we can write this in this way. Then we can rewrite at this point the storage equation, that is this. By introducing the Darcy law, we can rewrite, you see, this storage equation, incorporating the Darcy law inside this new formulation that has at the same time inside consolidation, the principle of Terzaghi has the conservation of mass and Darcy law. So has it inside all these three different behavior condensated inside one single formulation. And in general, the Darcy law usually gives a good description of flow in a porous medium, and again can be reasonably accurate. So again, inside the conservation of mass, we put two important things. One is the Terzaghi principle and the Darcy law. And so the storage equation is now this. We have some questions here before the last part. Okay, so this is the most important formulation, and even in a potential in an exam or whatever kind of things, when you will be asked what is the storage equation, you know that inside the storage equation there is this, the storage equation is this, but if you want to include also Darcy law, you will have this. That is, again, a good description of the physics. Now, as I said, we have the last, let's see, for today, 4 slides, so do not sleep now, please. We have the last important thing, but it's nothing different from what you have in structural engineering. So relax and just see what you already know. So in geotechnics, we are studying elements. We are studying equilibrium equation as well. So our element has to be considered loaded. So what happens if I load this element of soil? That stresses will be created inside the soil, inside the element. The only thing is that in the structural engineering, we have only one phase. We have only the solid. Here we have to consider all the 3 parts, as we said yesterday. So the complete formulation of a fully 3-dimensional problems require a consideration of the particles of solid mechanics, including equilibrium, compatibility, and stress-strain relationships. We will see later. In addition to this equation, the initial condition and the boundary condition must be formulated. These equations are presented here, again, for a linear elastic material that, again, is a very small part of geotechnical models. So you should already know that, again, from structural engineering, that if we have an element, these are the equilibrium equation, where Fx, Fy, and Z denote the component of a possible body force. In addition to this equilibrium condition, there are three equations of equilibrium of moments. These can be taken into account most conveniently by noting that they result in the symmetry of the stress tensor. So, I don't want to do again all what you already done in structural engineering. If we consider the rotation as well, we can have, you know, that tau or sigma x epsilon equal to epsilon x, epsilon z equal to z epsilon, and sigma zx equal to sigma xz because of the symmetry of rotation. And these stresses are in total stress. But here we were talking about the generalized Terzaghi principle. So if we remember that Terzaghi said to us that we have this relationship, we don't have only sigma, but we have sigma, comma, that is the intergranular stress, and this for pressure. So what happened if we put inside this formulation, the one that we call already, that we know already, inside the formulation, that the stress along the directions, of course, we can consider the Terzaghi principle. For the one that are connected with the rotation, we don't have to consider. And so, as alpha in Biot's coefficient is, as we said, 1 minus CS ratio Cm, we can introduce the Terzaghi principle inside this, simply considering the total stress as the effective stress plus alpha, that is called by the Biot coefficient, and P. And so we can consider the shear stress can, of course, only be transmitted by the soil skeleton. And at this point, the effective stresses determine the deformation inside the soil. As a first approximation of effective stress are now supposed to be related to the strain with the generalized form of Hooke's law. So again, if we consider a very, very small field, we can consider the material as isotropic, and so we can introduce similar relationships that you have already seen in your structural engineering course, where K and G are the elastic coefficient of the material, the compression modulus, and the shear modulus, respectively. And of course, they are related to the Lamé constant, lambda and nu, that you should already know. Lambda is K minus 2/3 G, and G is like nu. Do you remember this from your structural engineering class? Please say so.
Yes, yes, Professor. Those are familiar. Those are definitely familiar.
Very good. So it is, the only difference is that you have to introduce Terzaghi principle, right? The only things. And as I said before, K is the inverse of the compressibility of the porous media. So K is like 1 ratio Cm. So now you know the relationship between the geotechnics and structural engineering, because the soil at the end is a material as the concrete, as the steel. So we have only to change the property, but we can consider the same. But remember that we have inside the fluid. So there has to be introduced the Terzaghi principle. In soil mechanics, the compression model K and the shear model G are often used as the two basic elastic coefficients because they so well describe the two different modes of deformation, compression and shear. Especially we will see this in soil dynamics. So at the beginning of the next course, we will do the waves. We will see how it is important to consider these two parameters to understand how the waves behave inside the soil, especially with seismic engineering. That is, as you know, my major. So I will show, I think, in detail the importance of considering K and G in the propagation of waves inside the soil. The Vannon strain, the Vannon strain in the equation, yeah, he's 4.38, but is the sum of the three linear strain, of course, epsilon x, epsilon y, and epsilon z, that are, of course, related to the displacement component by the compatibility equations. These compatibility equations are the same system of equations that you should already know from structural engineering. Of course, the total number of unknowns are 22, 9 stresses, 9 strain, and this is similar to what you know. And also 3 displacements, but here we have also the pore pressure. So we have to consider also the pore pressure. And we have a total number of equations that are 22, 6 equilibrium, 9 compatibility equation, 6 independent stress-strain relationship, and the storage equation. So now you know why we talk about this most infamous equation. Because when you have the soil, you need to add an equation, because you have to think about the pore pressure. So basically, the study is similar to what you already seen in mechanics. But since we have the water inside potentially the water and the pore inside the material, we have to introduce the storage equation. So the system of equation can be simplified considerably by eliminating the stress and the strain, finally expressing the equilibrium equation in the displacement. And here we have what you should already know from, again, mechanical engineering. That is, of course, this way of writing the equation. When we consider the Vannon strain epsilon in this way, and the operator, that is this gradient, that is the sum of the double derivation. And in this way, let me see. Yes, okay. Yeah, so here we have definitely the system of the differential equations now consists of the storage equation that we know, the equilibrium equation, and these 4 equations are 4 variables. The 3 displacement, and P, that is the pore pressure. The volume strain epsilon is not an independent variable, as you know from this equation. The initial conditions are that the pore pressure P and the three displacement components are given at a certain time, for example, time equals 0. The boundary conditions must be that along the boundary 4 conditions are given. One condition applies to the pore fluid. Either the pore pressure or the flow rate normal to the boundary must be specified. We will talk about later on boundary conditions, but in general, I would like to introduce a little bit even here. The other two equations refer to the solid material, and either the three surface tractions or the three displacement components may be prescribed. Many solutions of the consolidation equation have been published, mainly for bodies of relatively simple geometry. And here, again, as I said, we will open a diaspora. I don't know if it's Espanol, English is not. We will open like an ocean of possibilities, in the sense that these equations that I propose here, I choose to show you these because they are very close to what you already done in structural engineering. But this is only a simplification procedure. There are more complicated solutions by Shipman and Wang, for example, or even more. Finally, the last slide for today is this, where I put together the equilibrium and the storage equation as a system, as we said, of differential equation with 4 variables, P, U, X, U, epsilon, and U, Z. You can see here these formulations. So definitely, you already know this from your previous studies. Now, from the lesson of today, you are able to derive the storage equation, where there is inside, remember, the Darcy and the Terzaghi principle. For today, we stop here. Tomorrow, you will behave. You will be able to see the second part. Do you have some questions, guys?
Professor, there is a question of Belen, I believe.
Okay, please. Thank you.
Professor, excuse me, it is possible that you can share this document with us, the PDF?
Of course, I will. Do you want right now, or I will share with you after the lesson, after I recorded the second lesson, but I will share just in a couple of hours because I will record the lesson right now for you. Yes,
It's
so
okay,
yes.
thank you.
And again, please, if there is some mistakes that could be possible, sorry, but I'm a human. If there is some mistake again, please tell me and I will modify, because again, it's the first time that I'm teaching in English this part. Okay?
Professor, just a quick question. Do you have Belen's email? Or
Yep.
maybe, okay.
I have the list because Francisco sent to me, but if you want, Belen, please, can you please send me your email? So I will send from now until the end everything to you instead to Francisco.
Mm-hmm.
It's okay, thank you. I'm gonna write you at your email. Thanks.
So I will refer to you instead of everyone else.
Okay, thanks.
Okay, thank you to you.
Thank you.
So again, thank you. And Belen, another thing, please, every time, especially, every time we will have the in presence lesson, remember to register, remember me to register the videos, because otherwise you will not have.
That's okay. I will care about it.
Okay, thank you, because I have always plenty of things, and as today I might forget. Thank you so much, and see you in the next lessons. Thank you. Have a good day to everyone.
All right, thank you, Professor. Have a nice day, you too.
Thank you.
Thank you, Professor. Bye-bye.
Thank you.